To truly grasp the foundational mechanics of modern networking, one must dissect the seven-layered conceptual architecture known as the Open Systems Interconnection, OSI model, which was standardized in 1984 by the International Organization for Standardization, ISO, to serve as an architectural blueprint that decouples software functionality from physical hardware infrastructure, ensuring that disparate computing networks can interoperate globally. At the absolute foundation of this stack sits the physical layer, Layer 1, an arena governed purely by hardware specifications, mechanical standards, and electrical, optical, or electromagnetic signaling interfaces, where structured network topologies like star, mesh, and bus configurations are established using physical media such as Category 6 unshielded twisted pair, UTP, copper lines, single-mode or multi-mode fiber optic cables, and wireless radio frequencies. This bottommost layer does not understand data structures, logic, or meaning. Its sole existential purpose is the raw transmission and reception of unstructured binary bit streams, which it achieves by converting logical zeros and ones into tangible physical phenomena through sophisticated modulation techniques like amplitude shift keying, ASK, frequency shift keying, FSK, phase shift keying, PSK, or complex line coding schemes like Manchester encoding, while adhering to precise mechanical specifications for pinouts, voltage levels, and connectors such as RJ45 jacks, LC-SC fiber terminals, and coaxial BNC interfaces. Immediately above this raw physical medium operates the data link layer, Layer 2, which introduces the first level of logical organization by transforming the chaotic stream of bits from Layer 1 into discrete, manageable data units called frames, a process structurally divided into two sublayers defined by IEEE 802 standards, the Media Access Control, MAC sublayer, and the Logical Link Control, LLC sublayer. The MAC sublayer interfaces directly with the physical media, utilizing unique, globally unalterable 48-bit hardware identifiers burned into every network interface card, NIC, known as MAC addresses. To manage physical topology addressing and arbitrate access to shared network mediums through contention protocols like Carrier Sense Multiple Access with Collision Detection, CSMA-CD, for legacy half-duplex Ethernet, or Carrier Sense Multiple Access with Collision Avoidance, CSMA-CA, for wireless 802.11 Wi-Fi networks. Concurrently, the LLC sublayer acts as an intermediary to the network layer above, identifying upper-layer protocols, synchronizing frames, and executing critical flow control and error detection routines via frame check sequence, FCS. Trailer that utilizes a cyclic redundancy check, CRC, polynomial formula to silently drop any frames corrupted by physical signal degradation or electrical interference before they can bubble up the stack. As communications expand beyond a single local area network, LAN segment, the network layer, Layer 3, takes precedence, executing the monumental task of logical routing and end-to-end packet delivery across vast, fragmented, and geographically distributed internetworks. Layer 3 abandons localized physical hardware addressing in favor of global logical addressing schemes, predominantly implemented via Internet Protocol version 4 IP4 with its 32-bit dotted quad notations and Internet Protocol version 6 IP6 with its vast 128-bit hexadecimal design spaces. Specialized network infrastructure devices operating at this layer, known as routers and Layer 3 switches, read incoming packet headers and continuously consult dynamic routing tables populated by sophisticated path determination algorithms, such as Open Shortest Path First, OSPF, or Border Gateway Protocol, BGP, to compute the optimal, lowest metric trajectory for data across the global internetwork. Furthermore, Layer 3 handles packet fragmentation and reassembly when a data packet encounters a downstream link with a maximum transmission unit, MTU, restrictions smaller than the packet's current size, alongside managing diagnostic and control messaging through the Internet Control Message Protocol, ICMP, which underlies diagnostic utilities like ping and traceroute. Bridging the gap between network-centric path selection and host-centric application processing is the transport layer, Layer 4, which is entirely responsible for the transparent, end-to-end transport of data between specific software processes running on distant host systems. Layer 4 accepts a continuous stream of data from the upper software layers, segments it into optimized portions called segments, when using TCP or datagrams, when using UDP, and appends a transport header containing logical identifiers called source and destination port numbers, such as port 80 for unencrypted web traffic, port 443 for TLS encrypted web traffic, or port 53 for domain name lookups. This process of port addressing enables network multiplexing, allowing a single physical device with a single IP address to concurrently run web browsers, email clients, and streaming applications without data cross-contamination. The transport layer's behavior is dictated by its choice of protocol. The Connection-Oriented Transmission Control Protocol, TCP, provides a hyper-reliable virtual circuit guaranteed by an initial three-way handshake, SYN, SYN-ACK, ACK, strict segment sequencing, mandatory error recovery via positive acknowledgement with retransmission timers, and complex dynamic flow and congestion control mechanisms using sliding windows to prevent a high-speed sender from paralyzing a slow receiver or congesting an intermediate pipe. Conversely, the Connectionless User Datagram Protocol, UDP, sheds all reliability overhead, error recovery, and handshaking to act as a highly lightweight, low-latency, best-effort delivery engine optimized for real-time applications where minor packet loss is vastly preferable to transmission delays, such as voice-over IP, VoIP, live video broadcast feeds, and competitive online gaming states. Sitting directly above this transport machinery is the session layer, Layer 5, which orchestrates the continuous lifecycle of connections between network applications by establishing, managing, synchronizing, and gracefully terminating the logical sessions or dialogues that exist between two endpoints. Layer 5 determines the communication mode of the session, whether it operates in simplex, one-way, half-duplex, alternating two-way, or full-duplex, simultaneous two-way modes, and manages session tokens to prevent conflicting, simultaneous actions during critical transaction windows. Crucially, the session layer embeds logical checkpoints and synchronization markers directly into long-running data streams. If an underlying network failure or routing collapse drops the connection midway through a multi-gigabyte file transfer or database replication event, Layer 5 allows the session to recover and resume data transmission seamlessly from the last verified checkpoint rather than forcing the entire operation to restart from byte 0. Once data passes through the session boundaries, it enters the presentation layer, Layer 6, which functions as the universal syntax translator and data formatter for the network environment. Layer 6 ensures that differences in data representation, character encoding sets, and abstract structures between the sending system and the receiving system are completely abstract and resolved before reaching the application software. It converts local, proprietary data structures into standard network syntaxes, translating character sets like EBCDIC or ASCII into universal standards like UTF-8, and parsing structured data formats such as extensible markup language, XML, JavaScript object notation, JSON, or abstract syntax notation 1, ASN1. Beyond translation, Layer 6 is the traditional structural locus for data compression algorithms that minimize the consumption of network bandwidth by packing media types into highly efficient formats like JPEG, PNG, MP3, or MPEG, and it orchestrates the intensive mathematical operations required for cryptographic encryption and decryption routines, such as those historically bound to the Secure Sockets Layer SSL and Transport Layer Security TLS handshake processes, protecting user data privacy before it is committed to transport. At the absolute apex of the OSI stack rests the application layer, Layer 7, which serves as the immediate user-facing interface, providing application software programs with direct access to comprehensive network capabilities. It is a critical distinction that Layer 7 does not refer to the actual standalone application running on an operating system, such as Google Chrome, Mozilla Firefox, or an email client, but rather defines the highly specialized network protocols that those software programs utilize to request, transfer, and render distributed information. This topmost layer governs iconic Internet protocols, including the Hypertext Transfer Protocol, HTTP, and its secure counterpart, HTTPS, for the request-response transactional mapping of the World Wide Web, the Domain Name System, DNS, for the distributed hierarchical mapping of human-readable hostnames to numerical machine IP addresses. The Simple Mail Transfer Protocol, SMTP, alongside the Internet Message Access Protocol, IMAP, for the multi-stage routing and retrieval of electronic mail, and the File Transfer Protocol, FTP, or Secure File Transfer Protocol, SFTP, for the structured navigation and binary transmission of remote file system structures. As an application process initiates a network action, data moves down this entire 7-layer hierarchy on the local host through a systematic architectural mechanism known as vertical encapsulation, where each successive layer views the entirety of the layer above it as an opaque data payload and prefixes its own control header, and suffixes a trailer in the case of Layer 2, before passing it downward to the physical wire. When these physical signals traverse the internetwork, hopping across intermediate switches and routers that de-encapsulate only up to the layer required to read MAC or IP addresses before re-encapsulating and forwarding, they eventually arrive at the destination host. The destination system then executes the inverse operation, known as vertical de-encapsulation, stripping away headers layer by layer from the physical layer up to the application layer, verifying the integrity and logical parameters of each layer's control fields until the original, pristine application payload is delivered completely intact to the receiving process. Through this elegant, modular peer-to-peer logical communication model, the OSI framework effectively isolates the vast complexities of global telecommunications, allowing a developer to write code for an application layer web protocol without ever needing to understand the underlying electrical engineering of the physical fiber optic lines or the wireless radio waves that will ultimately carry its data around the world.